little odd, but anyway, that's fine because I'm kind of rambling more than normal. Okay, quick review of this stuff again. So we're edging our way into adding potentials because, so again, as quantum is always such a funky thing. Remember I've been talking about the free wave, and that's because there's no potential energy, and everything is just this double derivative, which is kinetic energy, equal to a constant. Now, again, if we're in math class, we like to express things this way, which is actually junk. Now, I've written the Hamiltonian, so I'm going to make this meaningful, you write the wave function. Since this is the Hamiltonian, I'll use the symbol psi, which is generally reserved for the Hamiltonian. And when you have just the kinetic energy Hamiltonian, the solution is this. It has to be this. There is no other possible solution. But what happens is, as much as this is always right, notice that I don't have, what is A? What is B? What the heck is that? What is K? Well, K, is momentum. But what happens is, if we're doing, truly, what am I saying here? So truly, no potential. If we truly have no potential, question.
For B, isn't it negative IKX?
Yes, thank you. Yeah, mine's IKX. Yeah, thanks. What would that mean if I didn't have the different? Okay, so for truly no potential, this is what we've been doing at the very beginning when I kept calling the electron in outer space all by itself the free wave problem. And again, this is a solution, but you have to whittle it down because you have to know something. You have to know what's going on. I have to tell you that I am God, and I created an infinite universe, and I put one particle in it, and I caused the particle to move right. So in that case, particle is moving to the right, therefore the wave function is entirely a right-moving wave. So the point here is that you have to have descriptions of the problem to start whittling this down. Otherwise, this is great, but you can't really do anything else with it unless they start giving you information about what the heck it is you're supposed to be describing, which makes a lot of sense, right? Now, again, hopefully at this point you know that from the momentum operator, that is a right-moving wave and that is a left-moving wave. And the way I would solve A at this point is I would normalize it. And how would I solve K? Well, I have to give that to you. I mean, you have no way of knowing when God created a universe with a single electron and threw it, how fast did God throw it? Well, you have to know that or you don't know what K is. So again, you have to, it's nice and fine that this is the general solution, but by itself it doesn't really tell you anything. You have to know what you're describing. So for truly no potential outer space, I kind of, I have to tell you how fast it's going. A, of course, would then be the normalization constant, which oddly is 1 over the square root of infinity. But as I mentioned to you, the truly no potential, the free wave, the electron all by itself in the infinite universe problem is a very weird problem. Now, actually, there is one thing about that. I do want to point out, though, there's one cool thing about this, which is that, let's see, if you were to do the momentum, let's do it I don't have to do it this way. I don't have to do it this. Actually, yeah. Let me do it this way just for the hell of it. Let me do it the eigenvalue way. Let's see. I'm just doing it this way just because I felt like it. I could also do it the expectation value way, but I'm going to do it this way just for the hell of it. E to the I k x is h bar h bar k e to the I k x. Okay, so there's your momentum. Okay, let's do momentum squared. And this has to work because the Hamiltonian basically is the momentum. And so that's minus h squared, double derivative. There's no 2m because this isn't kinetic energy, it's momentum squared. Eigenfunction. Sorry. The normalization constant still needs to be there. Okay, so I've got minus h bar squared, I squared, k squared, which is h bar squared, k squared, a e to the I k x. Okay, now I want to point out something. So this is just a little practice with uncertainty principle. Okay, so this is related to the uncertainty. What is that?
Standard deviation.
This would be yes, this would be the technically the variance. So let's cast it as a standard deviation, which can be part of our uncertainty principle. And note that you're doing this problem for a particle in a box. So what is that? The answer is right in front of you. I've worked out each individual part. Just look at it. Huh? Now remember that eigenvalue, I did this the eigenvalue way. Maybe what's your little loss is I'm expressing this as the expectation value way, but they should be the same. So what's this?
So
That's
h bar squared k squared k equals kx.
No?
Average.
No, it's just h bar squared k squared.
Oh, I saw you each part. So
No,
it'll be
no.
1 minus, yeah.
No, that's the eigenvalue. So now remember that in an expectation value, what's great about it is the wave functions get wiped out, and you're just left with the eigenvalue. So okay, all right? That's the expectation value of momentum squared minus what?
Oh, hk squared.
No,
Parentheses h k squared.
and that is.
0.
Right, okay, so here's the thing, you have no uncertainty in momentum. That's the cool thing about a free wave, no uncertainty in momentum. Okay, now that you know this, and you also know that recall that the uncertainty in momentum in a certain position has to be greater than h bar over 2, and we went over that last time. Therefore, what is the uncertainty in x? You should be able to answer this without actually solving it. So if this is 0, what does that have to be roughly equal for this to be greater than some constant?
Infinite.
Right, it's infinite. It has to be infinite. And infinity times 0 can balance in some weird way. You remember in calc class, if you were ever asked what's infinity times 0, it's undeterminable. It could be 0, it could be infinity, or somewhere in between. So basically it's infinity. Okay, now the question is, does that make sense? Okay, a free wave, remember, this is a particle in an infinite universe. Where is it? So God created an infinite universe, took a particle somewhere in it, not that somewhere is definable in an infinite universe, and threw it, and it's gone on for all eternity. And eternity is also forever. So where is it?
Everywhere?
Everywhere and nowhere. Right, so in other words, you don't know. Right, the position is undeterminable. It's a particle moving at some God knows speed in a universe that never ends, and it's been doing that for all eternity. Right? Of course you don't know where it is. So you see, this all kind of makes sense. Not only is it doable, it also makes sense. Notice also, let's see, now I could also, let's think about what the wave function, let's do this, for the free wave. Okay, so this would be e to the minus ikx, e to the ikx, and what is this? What's that? Right, it's 1. So what the hell is that? Right? So again, the wave function is ill-defined, and oh god, yeah, and then I didn't even put in the normalization constant. Look at that, you know what I'm actually doing is I'm basically solving the normalization constant, which is of course infinity. So square root of infinity. Anyway, so I just want to point out that Yeah, just work a simple problem, but now let's get to the particle in a box. All right, now this is something that this is the unbelievably most snarky thing. So free wave, hopefully there's really not much to it. It does some weird things like this, like, okay, the momentum is well defined, that wasn't hard to do, but the position isn't defined at all, but then that kind of makes sense. And that's really all I can ask with this. There's just nothing else there to even ask. Okay, now to go forward to harder things, because that's what classes do, I'm now introducing potential energy. Notice that I said that this A e to the ikx, B e to the minus ikx is the solution when there's no potential energy. There is potential energy, but I'm still using it. Why? Why would I do that? So even in the case of potential energy, this is still the correct solution. Why do you think that would be in the particle in a box? Yeah?
Is it because you're just changing the A and B parameter?
Well, no, that's how you solve it. So, you know, this is kind of, again, your interpretation of quantum. You're just now learning how to interpret it. What's the wave function amplitude outside the box? Now remember, there's an infinitely high potential energy barrier outside the box. So what's the amplitude of the wave function outside the box?
Zero.
Right, because it would take infinite energy for this, let's call it an electron, to get outside the box. Okay, outside the box is where there's potential energy. Inside the box, there's no potential energy. What's the solution for when you have no potential energy? Right, it's this. So even though this is the solution for when there's no potential energy, when there is still potential energy, this is still the solution. Yeah, seriously, this is how it works. I mean, I can't do better than that. So, and we're going to see even more examples of that. So now what happens is when you run into this problem, just like when I said, no snarkiness, there truly is no potential energy, therefore the universe is infinite, there's nothing to run into. Fine, I have to give you some information and you whittle things down. When I start doing these tricks, particle in the box tricks, and we're going to do another trick today, then you do the same thing. You have to start adding stipulations like boundary conditions. The wave function has to be 0 at 0 and 0 at L. It has to be smooth and continuous. You start looking at the stipulations that are imposed by potential energy, and you start whittling down what A, B, and K are. So recall that last time I said the wave function at x equals 0 is 0, and therefore A is equal to minus B. And again, I'm just reviewing. And from that, I can already tell that the wave function has to be a sine kx. Now again, I mentioned to you that sine technically has A of 1 over 2i and B minus 1 over 2i. But I can tell you, and this is like me telling you this, the fact that A is minus B is enough to know that you have a sine function. I don't need to know that A is necessarily 1/2 over I and vice versa. This is good enough. Okay, number 2, the stipulation of the wave function at x equal L being 0 means that K is n pi over L. And that's what makes the wave function look like this. There you go. So that's a sine. So this wave function is sine pi x over L. Right? Now, that's for n equals 1. Now you can have n equals 2 as well, in which case you get a wave function like this. And then you can have n equals 3, in which case you get a wave function like this. Didn't plan that ahead. Anyway, so there you go. And of course, these are excited states. So, So there you go. It's all again, when I set up this problem, I made stipulations that have consequences, and I stipulated that the potential energy was infinite at 0 and L. From that, you should be able to realize that there's consequences, and that, these being them, and from them you actually figure everything out. Oh, and of course, then you can normalize as well. I didn't write the normalizations. That was a little stupid of me. Sorry about that. Notice that you're also seeing the quantum in quantum mechanics. All right, now that we've got the wave function in it, and sorry, I should have done the normalization. Remember, I told you that. You see, you just saw me do it. I told you the number one mistake you'll make with these questions is you'll forget to normalize it. And that will throw off your expectation values. It'll just completely mess up your expectation values. There's even a problem on homework like that. So when I normalize it, of course, it's 2 over L sine n pi x over L. Okay, so you've got everything worked out. What else do I want to say about that? Now, on your homework, what I have you do, and if you want some help on that, we can do a little bit in here, but you actually solve a lot of this with an online integrator, because you end up with sine x sine squared and all that. Okay, so in your homework, I have you working with a particle in a box, and you solve all this, and you show that it's consistent with the uncertainty principle. The other thing you can do with this is that you can also figure out, now that we figured out the wave function, really all of them, you're able to do this. And from this, as we did, I know I was kind of rushing towards the end, you can show, and I'll show this in the reduced form, you can show this. Okay, and what about this? You can now see the quantum in quantum mechanics. N equals 0 doesn't happen because that would result in a flat wave function. Sine of 0 is just 0. And that would correspond to a particle that's not, that's nothing in the box, so we don't really write a wave function for that because there's nothing to write about. So again, you've seen us set up a problem, establish boundary conditions, get wave functions. Notice I never use the Schrodinger equation, normalize it, never use the Schrodinger equation. Okay, now I use the Schrodinger equation, and then I can figure out other things like energy. And I can also see the quantization of energy. The energy comes in steps, right? So remember I was telling you that, I said this, I think I said this to you last semester, like last year basically. If I'm in a room, and notice I'm in a box, I am, I have walls in front of me and behind me, I can't go through them. That I don't walk at any speed, I walk at one speed, but if I want to walk faster, it's not, I don't continuously speed up, I'm only going in jumps, right? So there's no in between. You perceive this, you perceive me doing this, but it's not real. It's not real, I'm actually going faster in discrete jumps. It's hard to see because I'm very large, right, compared to an electron. Let's see, what else do we want to say? There's another thing, I didn't mention this before, and I don't think I want to make a big deal of it, but when it comes to these types of example problems, particle in a box, you find one thing, and I think I have this on your next homework. It turns out that Hamiltonians, any Hamiltonian we can ever come up with has this property. Let's say we're calculating the average energy. It turns out that there's this mathematician, Charles Hermite. Charles Hermite, back in like 1800, before quantum mechanics, is just a math guy, right? So he starts, they knew about math operators, they weren't things for things, they were just pure math questions. But this guy noticed, and I'm going to put this in the language of quantum mechanics, that for, here, let me write out the expectation value. Okay, and let's make this like the first excited state and that the ground state. So you, wait, sorry, what have I done? That's stupid. Okay, there's that. That's correct. Okay, now what happens if you were to do this with a different wave function? What if you were to do this? For one, what does that even mean? It doesn't mean anything, actually. This is mathematical junk. But what Charles Hermite noticed was that, again, for mathematical expressions that were equivalent to this, that he found that this was true for things that we know are quantum Hamiltonians. Okay, now this is probably a very confusing set of symbologies. Okay, so notice that this is basically, it's like the energy expectation value above, but I'm inserting a different, like, excited state here. So this is the ground state, there's the operator, and that's the complex conjugate of an excited state. This by itself, I don't know what this does. This doesn't probably do anything. This is just weird. So I don't know how Charles Hermite ever figured this out, or why he even thought to.
It's like a statistician type thing.
Yeah.
It's dealing with the complements of things.
Yeah, so this is the complex conjugate, and he switches the I and J. Right, so, and they happen to be equal. All the operators that you're going to see in this class behave this way. It's really a function of the operator. When this happens, because Charles Hermite discovered this, we say the Hamiltonian is Hermitian. And therefore, energies, really all eigenvalues, are real. Okay, so again, I am using the Hamiltonian operator as an example in this case. I can insert momentum operator, momentum squared operator, position operator. All the operators you're going to see in this class have this property. They have this weird symmetry, and I'm not going to make anything more of that. I don't know why the guy ever thought to write this down, but he did. A consequence is that all the eigenvalues, and I'm writing energy because I'm using the Hamiltonian as an example, all the eigenvalues are real. Now, versus having the letter I, that would be unreal. Right. Now, here's another thing. In quantum mechanics, if you were to do an eigenvalue equation and get an imaginary eigenvalue, then that is literally unreal. It's unobservable. So it's not necessarily something's wrong, but it is not something that can be observed by us humans. So you can imagine that you don't run into that often. So if you're measuring momentum, momentum is real. Momentum is measurable. Energy is real. Energy is measurable. That's because the operators you're using are Hermitian, and the eigenvalues, whether they're energy or momentum or position, they're all going to be real numbers, and literally they are real. So you can interpret that in the most literal manner possible. Now, one thing I'm going to have you do on a homework is this. Now, that's consequence one. There's a second. The other, this is the unmovable board. I'm going to write this down and I'll have to get rid of it. The other is that for any two wave functions that are not the same, okay, for any two wave functions that are not the same, this is zero. We call it overlap. This is zero. And there's another one, and you're familiar with this. I wasn't even sure whether I was going to write this down, but I've gotten this far, so I might as well write this down. Okay, that's another consequence. You've seen that one before already. And this is the property of orthonormality. Okay, so normality is this. And again, I actually introduced that really when we were doing Maxwell-Boltzmann, but Maxwell-Boltzmann and quantum aren't quite the same thing. So I showed you early on when we got to quantum to try to make you as comfortable with this as possible. And the first thing I said about wave functions, that wave function squareds are probability distributions, and so they integrate to one. Okay, this is the ortho part, that cross terms integrate out to zero. Now, the reason I'm bringing this up is we're going to run into this a lot. When we write out wave functions, when we get to multidimensional, you run into cross terms all the time. What's going to happen is we're going to have a lot of foils, like wave functions that are a plus b times a wave function that's c plus d, and you're going to have cross terms out the wazoo, and they're all zero. You need to know this because otherwise you're going to be spending hours and hours on Symbolab or Wolfram Mathematica doing integrals that equal zero. And great, you did it right, or you just recognize that because of this Hermitian thing, orthonormality, that they're automatically zero and you don't have to work on them. And again, you're going to run into that a lot. Okay, so anyway, and I don't think I had anything else to say about that other than to start giving you yeah, so again, I've covered about as much as I think I can on particle in a box, because you're going to do a lot of that, a lot of the harder ones on your homework. And although I certainly don't mind trying to work some questions in the next hour. And the time we've got left, so I'm actually going to go out of order in terms of how this class is. So sorry folks, I accidentally put this on the board I can't move, so that's, hopefully you got it. Watch the video. Now I want to introduce a new problem. And this one is going to be a flat potential. It's going to be flat for half the space. And there's going to be a little jump in potential energy for the other half. So let me just run that. Here's potential. And here's x. We're still one-dimensional. I think it really won't be next week. It'll be the week after that we'll start doing multi-dimensional. One reason I'm a little perturbed today is I actually decided to go out of order. Normally we do multi-dimensional today, but I kind of thought not, because this comes up later and this is still one-dimensional. And let's say this is at x equals 0. Question?
Is that one-dimensional though?
This is one-dimensional.
You're plotting x versus v.
No, it's one-dimensional.
In direction.
Well, so this would be two-dimensional. Right. So the energy is a function of two dimensions. So right. So you're right. It is. If I start drawing potential, then that technically this would be three-dimensional. I guess that's two-dimensional in the sense that the board is two-dimensional. But I've only got one dependent axis, so that's technically one-dimensional. And again, we'll say that this occurs at x equals 0. So obviously, right, if you ever get confused, one of the little things I just want to point out to you is if you're going to figure this out on your homework, it really matters when you set up these problems where you define little steps or barriers. If you define them at the best, like it's obvious, right? Make the step occur at x equals 0. It's kind of obvious that that's where you want it. If I made this like at x equals L, you can still solve. It's the same problem. It has the same solution, but it's going to be 100 times harder to solve, to work through all the calculus to solve it. So anyway, just want to point that out. So, and you're going to definitely figure that out on your homework because I recentered the particle in the box. Anyway, okay. So now I've got a flat surface. In the next hour, if we have time, I will show you that the wave functions are still, the wave function, because the potential is flat, is actually still this. Actually, I may get to it today. Actually, I think maybe I'll more likely get to it on Monday. Okay, so this is the general solution. It's still the general solution, actually just because the potential is flat. But now here's what the potential does. Here's what the potential does. Now get used to this because you're going to see a lot of problems. Like test 2 is going to have half the problems are going to be of this nature. What ends up happening is you get two different types of wave functions. You get one here and you get another one here. There's two regions, right? So in region 1 is a friendly area. That's a friendly area because it's what you've been seeing ad nauseum for nearly a month. It's a flat potential and the potential 0. Region 2 is slightly new because there is potential energy, but it's slightly old because the potential is still flat. When it gets curvy, trust me, that's when we're in the ninth level of hell. But it's still flat. The consequence is that there's two different wave functions on the left and right. That's the consequence. Okay, so here's what I can do. Now, we're going to work through this, so don't worry about this, but let me just warn you what is coming up. What is coming up is that once you get used to how to do this, I can kind of draw any potential surface, and then you should be able to figure out the wave functions like we did with the particle in the box by noticing that there's conditions imposed by the potential surface. Those lead to solutions to the wave functions, and then you can plug in the wave function into the Hamiltonian and get the energy. You can ask the momentum. You can apply any operator that you have. We have a few operators now. So that's, again, that's like the workflow of this. Okay, so what? Okay, now, so the thing we have to do is we have to start analyzing what the stipulations are in the wave function in region 1 and region 2, and hint, hint, they have to be smooth and continuous, remember that? So the wave functions are going to have to, like, they can't be disconnected, and they actually have to have the same slope, because that's what's meant by smooth and continuous. And what else? And what else is, I also have to give you a little bit more information on this potential surface. Because this is, in some ways, this potential surface may be actually kind of easier than the particle in the box, but we usually do this 1 second because it's slightly harder to solve. Intellectually, it's a little bit more akin to the free wave. The free wave is easy. It ends up being a little harder to solve. That's why we do the particle in the box. But anyway, like the free wave, I have to tell you a little bit more. I got to tell you, like, God created a universe with a single particle, and in the middle created a barrier. So that's what you have to be told. And one more thing. You have to be told that the particle started in region 1 and was thrown towards region 2 with a certain energy. Again, you can't, drawing this potential surface isn't enough for you to really do something with this. To figure out what A and B and K are. That's what I mean by you're trying to do something with this. I have to give you additional information. I have to tell you that the wave function originated on the left, it was thrown at the right side, and it had a certain energy when it did so. Okay, now here's why I have to tell you that. So again, you can assume that the potential is the y-axis. I'm going to start drawing wave functions. Remember that when I do this, I'm actually doing two things. I have two y-axes. I have the potential energy, and I'm going to draw the wave function on top of it as well. Okay, now, in region 1, it is a particle that started out moving to the right. That is a right wave. Now again, that's why I have to tell you that. I have to tell you that it was a wave moving to the right, and that is the right wave function. However, it's going to hit the wall, and it may bounce back. So that makes this a reflection. Now, I start out with this because, again, I am God, and I get to tell you how I created the universe and how it all started. It started with a single particle, and I threw it to the right, and therefore, this is its wave function. Eventually, it will hit the barrier, and it may reflect. And so I know that this is the reflection because I didn't start this universe out. I started it out with it moving to the right. If it ever moves left, it only did so because it bounced off. Now that means that the ratio of B over A, by the way, is related to the reflection. Like how much of it was reflected, by the way. Hopefully that's kind of obvious. Okay. Now, based on what I just described, there's a stipulation for region 2. One is that it hits the barrier and goes over. Okay, if it hits the barrier and goes over, now I have no reason to think that the normalization constant is going to be the same, so I'm going to give it a prefactor of the letter C. If it gets over the barrier and is moving right, it'll do so probably with a different momentum, and that means I now have to realize it may have different momentums left and right. So I'm going to have K1 momentum on the left and K2 momentum on the right. Now again, let's see. And then what else? What else? What do you think? Huh?
Or it might hit the barrier and never go over.
Well, we don't know that yet. So here's the thing. In terms of should I have it go over the barrier, I told you that God threw this electron at the barrier with a certain energy. I didn't say how much. Now, if it doesn't have enough energy to go over the barrier, it's probably going to reflect back. We're not going to say that it's destroyed or anything. It'll just reflect back. If it has enough energy to go over the barrier, it will, probably, and therefore it's moving to the right. Now, okay, so it's moving to the right. Now, what do I put here? The D, what?
No, nothing. Nothing.
Why?
Because there's nothing for it to make it want to go backwards on the right side.
Right, there's no D wave. Remember, this guy only appears because when God threw it to the right, it might bounce off the wall and move left again. If it gets past the wall, I haven't drawn any more barriers. So it'll keep going. So there is no D wave. Now, another thing is, the reason I write different Ks is that it has a certain amount of energy over here. If it gets over the barrier, clearly its energy is going to be less because some of that energy gets used up getting over the potential. You know, if you're running up a hill, by the time you're at the top of the hill, you're moving slower. You have less momentum. That's just horse sense, right? So that's why we have different Ks. Now, let's see, how am I doing on time? Okay, so with that, I'm going to then prove the general form of the wave function. So I've given you a lot now. I've given you quite a bit to figure out what the wave functions are. And then, yeah, let's do that. But when you run into this, you're always going to have to do things in terms of regions. You're going to always have to do two different analyses, region 1 and region 2. So in region 1, the wave function is e to the ikx e to the minus ikx. K1, sorry, that's important. All right, now what you can do is, and you already know this. We've done it a couple of times, and you should be able to do this. All right, we know this. And what you can figure out from here, I mean, I wrote this down just a second ago. H bar squared, K1 squared over 2m is equal to, so this is what you get over here, so that's equal to the energy. And then what you can do, so remember that I set up the problem, I've added some conditions, and what you can do from that is figure out what the wave function is. So notice that what I'm trying to do here is I'm trying to figure out what K1 is. Because I've got an equation, and the only thing I don't know is K1. Okay, so I can solve for K1. So K1 is 2me over h bar squared. Square root. Okay, is that right? Yeah. Okay, so there you go. Now I can write the wave function. Oh God, this is painful, but anyway, it has to be done. 2me over h bar squared x. Is that ix? Ikx. And I tell you what, let me worry about that later because we're kind of running out of time. Let's do part B. Because the next thing we have to do is figure out A and B. Okay, part two. Now this is where it gets a little bit more interesting. So I've got the wave function in region 2. Symmetry bothers me of c e to the I k2x. Okay, where this is different is that the Schrodinger equation is now different. The Schrodinger equation is different in that we've got kinetic energy. I'll just go ahead and throw in the wave function, plus potential energy, which is just some value that God has to tell you what that is, times the wave function in region 2. And of course, that's equal to the energy. Energy is not created or destroyed, so that's still equal to the energy. Now, the simple thing is, actually all you're doing is you're going to bring this over here, since the potential energy is just a number. What you end up with is solving this, h bar squared over 2m, double derivative. And what you're going to notice is is that you've basically got the same equation as what we have on the right side. The left side is the same equation on the right side, except that the energy is less. Right, so what do you get from that? So you get K2 is square root of 2m E minus V naught over h bar squared. Sorry, this isn't symmetric enough. There we go. There you go. So it ends up being like really kind of easy. You just have, you still have momentum. And 2me over h bar squared, square root of 2me over h bar squared. You've seen this a couple of times. And if you don't remember it, I just derived it. I mean, this is kind of silly at this point, right? And when you have a potential, it actually ends up being kind of easy too. You just have less energy. It's really quite simple. So now what? How am I doing on time? Okay. All right. Let me tell you what we're going to do next time, because I'm kind of out of time. Now that you have this, what you have to do is solve for the A and B part. So remember that I set up a potential barrier. I put in all these stipulations. I tell you that the particle's moving to the right. It might bounce off the wall, it might go through. That's how you figure out the form of the wave functions. You figure out K1 and K2. But now you've got to get A and B. Now the way to do that, here I'll just redraw it, is you can imagine you might be in a situation like this where there's a wave and it goes into the barrier. Maybe it decays if it doesn't have enough energy. Or it might do something like this. Now it doesn't matter which one it is, I'll explain why. Maybe it has a lot of energy. Maybe now notice that I'm drawing this wavier. Notice I'm drawing it wavier. That means that it has more kinetic energy. And maybe and notice I've also drawn it above the barrier. And so what could happen is it can penetrate the barrier. It'll have a longer wavelength because it has less momentum, less energy. There you go. Now, how does this solve A and B? Because now it's like, oh great, now I've got two wave functions. I've got a wave function in the first region, a wave function in the second region. Oh, awesome. And now I've got two different situations. Too little energy or too much energy. So what the hell? So now I've got to solve four things. No, you don't. No, you don't. Tell me about what's happening right there. Or here. Because in either, there's two things that are the same about both of them. Let's think about wave function 1 at 0. What's that equal to? In either case. Huh?
Equals to the second one at 2.
Right. So remember how we did particle in the box? I said at x equals 0, the wave function had to be 0. This is a little different. It just has to be, the left has to equal to the right. That's continuous. Now what does smooth mean? Remember I said wave functions have to be smooth and continuous?
Their first derivative section.
Left side? Yeah, the first derivatives also have to be 0. There you go. So that's the smooth part. Right, no kinks. Remember, if there's a kink in the wave function, then that's a major problem. That would actually say that you have tremendous amounts of kinetic energy to have a kink in the wave function. So, okay. I gave you enough information to give Ks. Now you should know that wave functions are continuous and smooth. And from this, what you're going to get is A, B, and C. You get A, B, and C using these boundary conditions, and then it gets kind of neater. Then you got to think about, well, what do I do with that? Right? Well, you can solve the Schrodinger equation, you can do yada yada yada, or you could do this. You can solve for a ratio like this. What would this be equal to? I just said it a while ago. What's B over A? Now, B is the wave that moves left, how much wave moves left, and A is the wave that was originally moving right. So this is the amplitude of how much gets, well, now what do you call it if it bounces backward? There's a word for that. Begins with R. Recoil, think of a better word. Reflection. Right, this is the reflection. The amplitude that bounces off the wall versus what hit it to begin with, this is the reflection. Now, I hate to do this to you, but it's actually the square root of the reflection. It just is. I kind of have to just tell you that. Now, the reason that that's true is that because, remember, wave functions squared are probability distributions. Wave functions don't actually mean anything unless they're squared. So that's why B over A is actually the square root of the reflection. So that kind of makes sense. Okay, in which case, though, regardless, what is 1 minus B over A? What does that equal to? Percent reflection, percent... There's another word for that, begins with the T. Percent transmission. Are you sure?
Square root of it.
Square root. Okay, so next time we'll start from here. I'll remind you what the wave functions are with their K's. Then we're going to do the derivatives, and we're going to be able to solve for B over A and 1 minus B over A and get the percent reflection transmission. So sorry, I know I went over, I always do. So again, I hope you come back in the next hour so that we can, a 10-minute break. Do whatever you want, or